Okay, Calculus 2 students, are you alert and ready to take notes? We are about to learn the hardest formula for the semester. Are you ready? Here it comes. The derivative with respect to x of e to the x equals e to the x. Okay, obviously I was just kidding. This is a very simple formula, probably the easiest one we're going to learn all year, but it's actually very profound. The derivative of the natural exponential function is the exponential function itself. That means if I want to find the slope of the exponential curve, it's given by the function value of the exponential curve. Now, where does this formula come from? We're actually going to build our understanding of this formula on the derivatives of natural logarithms that we've already learned. We also know that the natural exponential function and the natural logarithmic function are inverse functions. So they obey all of the properties and relationships that we've studied for inverse functions. So we can say, recall from properties of inverse functions, and specifically, I'm referring to the fact that you can compose two inverse functions in either order and always obtain the original argument. That is, f of f inverse of x equals x, and f inverse of f of x equals x. If we apply that to the exponential function and the natural logarithmic function, we end up with e to the natural log of x equals x. That is the natural log function plugged into the exponential function. And the natural log of e to the x, this is the natural exponential function plugged into the natural log function. When we compose those in either order, we end up with x. Now, let's look at that second equation. We can differentiate that to derive this derivative formula. So, differentiating the second property, WRT with respect to x, we obtain the following. We have the derivative with respect to x of natural log of e to the x equals the derivative with respect to x of x. So again, we're just looking at this property and we're differentiating both sides with respect to x. So as we have learned, when we differentiate a natural logarithmic function, we take the argument of the logarithm and we put it in the denominator and we put the derivative of that argument in the numerator. Well, other than the fact that I have written the formula here, we're working on the proof, so we're trying to derive this formula. So for now, we'll say we don't know what that derivative is. I'm going to write it as the derivative with respect to x of e to the x. Okay, so we have 1 over the argument times the argument's derivative. Recall that multiplying by the derivative of the argument is equivalent to putting that expression in the numerator. Now, on the right side, it's very easy. The derivative with respect to x of x is 1. Now, this is what we're looking for. This is what we're trying to establish. So I'm going to go ahead and solve this equation for that expression. We can easily solve for that expression by multiplying both sides by e to the x. We would end up with derivative with respect to x of e to the x equals 1 times e to the x. And that establishes the proof. So the derivative of the natural exponential function is the natural exponential function. Now, another case that we may run into is not just e to the x power, but e to a function of x. If we run into a function of x in the position of the exponent, then we're going to make a copy of the exponential function exactly as it appears, and then, according to the chain rule, we'll multiply by the derivative of the exponent. So another way to look at this, the derivative with respect to x of e to the u is e to the u times u prime. Again, pay attention to the details of the notation. I'm differentiating with respect to the independent variable x, so automatically we recognize u is representative of a function of x, which of course calls for the chain rule. So this is a very simple differentiation formula. Let's practice it with a few examples. Differentiate the following functions. Y equals 3 times e to the 1 minus x squared. Notice e has an exponent that is a function of x. So we can call this derivative, we can call it dy over dx. We can call it y prime. All of those are acceptable. We're going to make, first of all, we have a constant coefficient. So that constant coefficient filters through to the derivative. Then we're going to make a copy of the exponential exactly as it appears. And then, according to the chain rule, we're going to multiply by the derivative of the exponent, which in this case would be negative 2x. So comparing this to our formula, we have e raised to a function of x, which we can call u. And here is the derivative of that exponent. That takes care of the calculus, but we do want to simplify this as much as possible and apply a little bit of algebra here. Generally, when we have exponential functions, it's nice to keep the exponential function to the right of the expression so that you don't accidentally combine the exponent and what's supposed to be on the baseline here. So notice we've got 3 factors being multiplied. We can multiply those in any order according to the associative property. So I'm going to multiply the 3 and the negative 2x together. That's going to give us a negative 6x, and it'll be convenient to write that at the left simply because it makes it more readable. And then we have e to the 1 minus x squared. So there is the derivative of the original function. Let's try example B. Y equals e to the 5x times x squared minus 3x. Notice we've got the product of 2 functions of x, so of course we're going to need the product rule. Now, just for variety, to make you realize there's several ways to denote a derivative, let's call this one dy over dx. Remember, that's called Leibniz notation. So we're going to follow the pattern, first function times the derivative of the second plus the derivative of the first times the second, where we've got our natural exponential as the first function and a polynomial for the second function. So we keep the first function the same, and we multiply by the derivative of the second. Now watch your baseline here. Make sure that the exponent and that polynomial factor do not accidentally combine. So the way you write it sometimes affects how you think about it. Plus the derivative of the first function. Now the first function is an exponential, so we make a copy of the e exactly as it appears, and then we multiply by the derivative of the exponent, which in this case is 5. And then finally, we keep the second function the same. So we've accomplished the product rule. We applied the formula for differentiating an exponential function. Our next goal is to simplify this expression. Usually the challenge comes in the algebra. The algebra sometimes tends to be harder than the calculus. So I want to view this as 2 separate terms. Okay, and I'm not going to multiply everything out. Instead, I'm going to recognize they have a greatest common factor of e to the 5x. So I'm going to factor out the e to the 5x. That's going to leave behind 2x minus 3 plus 5 times x squared minus 3x. Just think about it. If I were to analyze this derivative for critical values, I would definitely want it factored. So generally, factoring is a great way to simplify your derivative. Now, let's combine everything that we have there in brackets. I'm going to demote the brackets to parentheses. We have 2x minus 3. Let's go ahead and distribute our 5. 5x squared minus 15x. So we have an exponential function, e to the 5x, times a polynomial. Let's go ahead and write this polynomial in descending order. So I'm going to start with 5x squared minus 13x minus 3. I don't believe that polynomial factors, so there is our simplified derivative. Now, the next example is a natural logarithmic function, and we're looking for the first derivative. So let's call this one, actually before we differentiate, do you see anything we could do to first simplify this function? Notice if I differentiated this directly, I would have 1 over this big scary argument times the derivative of that argument, which would require the quotient rule. But if we first use our algebra and we apply logarithmic properties, we can simplify this function before we differentiate. So I'm not yet going to call this y prime. This is still y. We're doing algebra, not calculus here. We've got the natural log of a quotient. So we can rewrite this as natural log of the numerator minus natural log of the denominator. That sets us up nicely for finding the derivative. I'm going to call it dy over dx. When we differentiate a natural log function, we put the argument of that natural log in the denominator and the derivative of that argument either in the numerator or multiplying by that derivative. So the derivative of 1 plus e to the x is 0 plus the derivative of e to the x, which is e to the x. Let's apply the same thing for our second logarithm. We're going to put the argument of the logarithm in the denominator and the derivative of that argument in the numerator. Notice the 1 minus e to the x, we've got a negative coefficient on e to the x, so that negative 1 coefficient filters through to the derivative. So one thing we could do to simplify, of course, would be to cancel those double negatives. And then, again, if we needed to analyze this derivative, it would be nice to have it as one cohesive fraction. So let's go ahead and get a common denominator and combine those two fractions. So the derivative of y with respect to x will have a common denominator of the product of our two different denominators, 1 plus e to the x and 1 minus e to the x. Now, looking at our first fraction, the original numerator was e to the x, and if I compare this denominator to this new denominator, we have gained a factor of 1 minus e to the x. So our old numerator needs to gain that factor as well. We've got a plus in between our two fractions. Next, we're going to look at this denominator to our new denominator. We've gained a factor of 1 plus e to the x, so the original numerator also needs to gain that factor 1 plus e to the x. Okay. You might think to distribute the e to the x in both of those parenthetical elements, but that's actually not what I'm going to do. I'm going to recognize I've got two terms in this numerator, and both of those have a greatest common factor of e to the x. So let's factor out the e to the x. Now, when I take the e to the x out of that first term, that leaves behind 1 minus e to the x. And when we take the e to the x out of this second term, that leaves behind 1 plus e to the x. That was a pretty good move. I think that'll be easier than the distribution that we talked about a minute ago. So we have 1 plus e to the x, 1 minus e to the x in the denominator. So notice inside parentheses here, the negative e to the x and the positive e to the x cancel. And that leaves behind a 2 in parentheses, so we could call this 2e to the x over 1 plus e to the x times 1 minus e to the x. And that is our first derivative. In that problem, we not only got to practice the derivative of the natural exponential, but also the derivative of the natural log. Let's try example number 3. Find dy over dx for x times e to the y plus e to the xy plus equals e to the xy. So we are looking for the derivative of the dependent variable y with respect to the independent variable x. But notice we have an implicit equation. So you can probably imagine we're going to need to use implicit differentiation on this equation. To be very clear about the independent variable, I'm going to write the plan. We're going to differentiate both sides with respect to the independent variable x. Okay, we are set up and ready to go. Let's differentiate term by term. Now, looking at our first term, x times e to the y, we actually have the product of two functions of x. Remember, y represents a function of x. So we are going to need the product rule on that first term. So we'll take our first factor x times the derivative of the second factor. The derivative of e to the y is e to the y, but because y is a function of x, I need to apply the chain rule here and multiply by the derivative of the exponent. Plus, now we have the derivative of the first function, which is just going to be 1 times the second function as is. Now, because I didn't differentiate this term, no dy over dx is necessary. So make sure you see that these two terms are the derivative of that first term only. Now we're ready to differentiate that second term, e to the x plus y. Think about the rules for differentiating a natural exponential. First, I'm going to need to make a copy of the exponential exactly as it appears. And then, according to the chain rule, since the exponent is something other than just an ordinary x, I need to multiply by the derivative of the exponent. Well, the derivative of x plus y, first we find the derivative of x, which is just 1, and then the derivative of y is dy over dx. The right side, we're going to apply a similar approach. We're going to make a copy of the e exactly as it appears, and then we're going to multiply by the derivative of the exponent. Well, notice the exponent is the product of two functions of x. Remember, y represents a function of x. So to differentiate that product, of course, we're going to need the product rule. So we have the first function, x, times the derivative of the second, which is dy over dx, plus the derivative of the first function, x, which is 1, times the second function, y. Okay, we are done with the calculus part. The next part is we need to solve for the derivative dy over dx, and I have it in several terms. So my next goal is to start collecting every term that has a dy over dx on one side and everything that does not have a dy over dx on the other side. So I'm going to begin by multiplying this e to the x plus y to break up those parentheses, and I'm going to break up these brackets over here with the distributive property as well. So we end up with x e to the y times dy over dx, no change on that term, plus, I'm going to simplify that term and call it e to the y. Distributing here, we have e to the x plus y times 1 plus e to the x plus y times dy over dx. Distributing on the right side and writing it in a nice readable order, I'm going to call this x e to the xy dy over dx plus y e to the xy. Now I'm going to collect all of the terms that contain the dy over dx on the left side. So these terms are going to stay. This one I'm going to subtract from both sides. These two terms need to go to the right. I'm going to subtract those from both sides because they do not have the dy over dx term. So we end up with, let me see if I can fit it over here. On the left side, we have x e to the y times dy over dx plus e to the x plus y times dy over dx. Now I'm subtracting this term from the right side to the left side. X e to the y dy over dx, and this is going to equal what we have over here on the right side is y e to the xy. We're going to subtract e to the y and e to the x plus y. Okay, so I'm just rearranging terms from one side to the next. Now, on the left side here, I've got three terms that contain the dy over dx. So I'm going to go ahead and factor that out. We have dy over dx times x e to the y plus e to the x plus y minus x e to the xy. And we have the same thing left over here on the right side. Y e to the xy. I think we needed a little more room for this problem. What do you think? Okay, so to finish up, we need to solve for dy over dx. Essentially, I'm going to divide both sides by this term. So we end up with the first derivative dy over dx equal to y e to the xy minus e to the y minus e to the x plus y divided by this factor coming over here from the left, x e to the y plus e to the x plus y minus x e to the xy. Now, I don't know about you, but that's the most fun I have had all day. That is beautiful. Now, remember, we started with an implicit equation, so we ended up with an implicit derivative. That means the x's and y's are mixed up together. So this function, this equation probably does not graph as a function. That is something that passes the vertical line test. So the slope would not depend on x alone, but the slope would depend on both x and y. Now, are you thinking, wait a minute, you said this is going to be the easiest formula we learn all semester. Well, the basic rule is very easy. This one turned out to be a little bit complicated with the algebra, but that completes this video.